the next talk comes from Ruben, and I'm just going to ask you all to listen out for something. Can you hear that? Can you hear it? Is that the silence of payments? I hope that I'm really sorry for the dad joke. I'm really hoping that Ruben is going to explain that to us all now. So Ruben, you good to go? Slides on the screen. Yep. Can we welcome Ruben to the stage for a talk called Silent Payments?
So I promise I won't be silent during this presentation and talk actually about this talk. So I'm going to talk about silent payments and briefly summarize. It's basically private and non-interactive payments. So the essential problem is that we currently have in Bitcoin basically two common payment flows. One of them is that you actually give someone a fresh address and then they pay you. But the problem with this is that it's interactive. So if I have a friend and I want to pay them, and let's say I want to pay them multiple times, then every time I want to pay them, I have to say like, hey, give me an address, they give me an address, and then I pay them. So this is kind of cumbersome. There are ways to automate it, like BTC Pay Server, but those have issues too, mainly the gap limits, where somebody might hammer your server, get a ton of addresses from you, and that ends up causing problems. And so then the second option is one that we all hate, but is an option nonetheless, which is address reuse, right? I could have a single address, give it out to everyone, and everybody pays me on that address, but now you don't have any privacy whatsoever. Everybody can see that you are getting paid. And in fact, it's even bad for the sender because let's say I'm someone that the government doesn't like and I'm receiving payments, then the fact that you sent the payment to me might also implicate you. So the real question here is, can't we do both? Can't we have it be non-interactive, where you don't have to actually ask for a fresh address, but still retain the privacy? And that is what silent payments is about. And I would say that this is essentially how people that don't know Bitcoin think Bitcoin works, right? They think you just have a bank account or some kind of number, and everybody just sends money there. But actually, because of this, it's a little bit more cumbersome. But this goes back to actually enabling having a single address and still receiving payments and still retaining the degree of privacy you would expect from handing out fresh addresses. So this scheme relies on a diffie-hellman, which is basically a way to generate a shared secret. I'm going to go through this first without any cryptography, and then briefly show the cryptography for people who do sort of understand this. But essentially, the way it works is you have a public key, and that's generally how Bitcoin works. You have a key, and you publish it, and you say, this is my key. If you want to send a payment, this is the key that you're going to use. And then the sender somehow communicates to the recipient, hey, I have a key too. And with those two keys, you can generate a shared secret. So a shared secret basically means that you have the key from the sender, you have the keys from the recipient, and they can do some math in such a way that they generate a unique number that only the two of them know, and people outside of these two parties will not know what this number is. And with this, you can now generate a public key that you can send money to that the recipient controls. So part of the key is the shared secret that you both know, and part of the key is something that only the recipient knows. So to briefly go through the math, and it's okay if you don't understand this, you have two public keys. The shared secret basically means that you have the private key multiplied by the public key of the other side generates the same thing. So either the private key of A multiplied by the public key of B, or the private key of B multiplied by the public key of A. It ends up with the same shared secret. And you generate a key that only the recipient controls, recipient being A here, by, at the end, generating the address by adding A to it, because A, big A, the public key, is something that B, Bob, the sender, does not know. So silent payments in a nutshell, basically, the way it works is the recipient openly publishes their key. And so it doesn't really solve for the issue where you still have to know that the key actually came from the recipient. So you have to trust sort of the source from which you obtained that key, but that's sort of a general issue that's out of scope for silent payments. But you could imagine you have a Twitter account, you have your address there, you have your silent payment address there, and that's where people get the key from. So then the sender key, and that's sort of been the general issues. Well, how does the sender communicate their key? And the way it's done here is that we look at the on-chain transaction and we say like, well, whenever you send money to someone, you're using a key. So why don't we use that key to generate a shared secret? So within the transaction, you're going to have an input, and the input is going to have a public key. And then with that public key plus the openly published recipient key, you generate the shared secret and you generate the silent payment address. So the nice thing about this is that this has no extra on-chain data whatsoever, right? You don't have to, and this is compared to some other schemes where there's some kind of notification transaction that you have to send first in order to make sure that they know the sender key. That is not the case here because we're utilizing the data that's already there on the blockchain. This is very strong privacy preservation, also because you don't have to identify yourself as a sender. Right? So if I want to send a payment to someone, I want to send multiple payments to them, they don't actually have to know it's me. They don't have to know it came from the same person multiple times. So this gives very strong privacy guarantees. And this is better, for instance, than manually asking someone for an address multiple times, and then in doing so, you've identified yourself 3 times or however many times to the recipient. That's not the case here. So you can actually send quite anonymous donations. So the big downside is the scanning requirement. So essentially, because you're using an input key, the recipient doesn't really know which transaction to look for. And so the answer here is to just look at every transaction, do the math, and see if you received the payment. And in general, if you're already running a full node, the extra work that you're doing is not that bad. But for light clients, this can be tricky, and we'll get into that in a minute. I have sort of a pretty neat way to sort of make this work for light clients as well. And another downside is that there's some Coinjoin complexity that we'll get into. So generally, the weaknesses here are so the scanning cost, right? And we have ways to minimize that. There's some Coinjoin issues I'll get into. Light client support is something we'll get into. And there's a final thing called payment labels, and that's sort of a way to distinguish when you're receiving multiple payments, the purpose or the reason or why someone paid you. So currently, if you receive a payment on a silent payment address, you would just know, okay, well, someone paid you, but you don't really know why they paid you. And if you want to make that distinction, if you want to receive payments for different reasons, payment labels are ways to sort of enable that. So it's already good without, like, even with these issues, like just the basic concept that I just explained is already quite good. But we can do better, so let's do that. So the scanning cost, so that's the first one, right? That's sort of the one where all the work is, basically. And so the first thing to notice here is that you don't really have to scan any, you don't have to check transactions that occurred before you generated your silent payment address. So if you start using silent payments today, you generate an address today, and you start checking from today every transaction from now into the future. And then the second thing is that the proposal as it currently stands will only allow for taproot outputs. So if the transaction doesn't contain a taproot output, you don't have to check the transaction. And because taproot is currently not being utilized a lot, but is expected to grow, we sort of have a reset here on the amount of work that you have to do. Currently, because taproot is not that much in use yet, there's actually not a very high scanning cost. And so one thing here also to point out is that the scanning and the spending can be separated. So you could have a key for scanning, for noticing that you're getting paid, and you can have a key for spending. And this is important for hardware wallets where you might have an on-chain key that does the scanning, an online key that does the scanning, so a key that is on your computer actively checking whether or not you got paid. And then if you actually want to spend, you connect your hardware wallet and you use the spending key to actually spend that output. So then in the worst case, if your computer gets hacked, you lose your privacy, but you don't lose your funds. So another sort of way to optimize the scanning cost is instead of using a single input in a transaction, we can actually combine all the inputs in a transaction, and this allows you to basically, you could either have one expensive operation in order to sort of do this calculation, and that's a elliptic curve multiplication. And by combining all the inputs, you only have to do it once for a single transaction, as opposed to do it once per input. So this basically halves roughly the cost if you on average say that a transaction has 2 inputs. And so then another thing you can do is, instead of scanning every transaction, you can say like, well, why don't we scan the UTXO set and really minimize what you check for. And the downside here, the one obvious downside is that you don't find your history, right? So instead of going through every transaction that ever occurred and seeing like, oh, this is also payment, you only check basically the transactions that have unspent outputs. And so you're only finding the funds that you haven't spent yet. And so definitely you will have full access to your funds, but you might want to know whether you received a payment somewhere in the past and you spent it again. If you want to know that, then UTXO set scanning is not for you. And this may need some kind of database to speed up the lookups that are required, but we're currently not certain whether or not this is required, and it would be nice to be able to do this without a database. So to give some brief examples as to what this would look like. So here's a simple transaction with 2 inputs, 2 outputs. So first, in the case of just having a single input to look at, let's say input 1 is the key that you use to generate the payment, and output 2 is the resulting output, and then maybe output 1 would be the change address or something. So let's define X as the silent payment key, so that's the key that I would have in my Twitter profile or something if I want to get paid. And then output 2 is generated by basically generating a shared secret, which is the key of input 1 multiplied by X. And you turn that into a public key by multiplying it with G, and you add X to it at the end to make sure that only the recipient of the person who controls the silent payment key can actually spend it. And then on the other side, instead of having the input being the private key, you take X as the private key, and you take the input as the public key, and you generate the same secret. So this is how the recipients would figure out that they got paid. So in a Coinjoin, there's one sort of issue that I want to point to here. And that issue is that, so the math here is exactly the same, right? So the issue here is that the recipient, if you have only a single input that is used to generate the silent payment address, is that the recipient now knows which input they were getting paid from. And if you think about a Coinjoin, right? A Coinjoin is a transaction with multiple people adding their own inputs and outputs. And now the recipient can look at this, generate the silent payment address, notice that they were getting paid, but now it's linked to their input, to the input of the sender. So the recipient now knows that input 3 is which they receive money from, whereas with a regular Coinjoin, they wouldn't know whether input 1, 2, or 3 is responsible for sending money to output 2. So this is not ideal, and so we can solve this. In the case of the Coinjoin, we can solve this by taking all the inputs, and like I mentioned earlier, this is also a speed up, incidentally. So it really sort of neatly resolves both issues. Where now, as you can see here, you have the private key X multiplied by the addition of input 1, input 2, input 3. And so there's only one multiplication, which is the important part, because the multiplying by a public key is sort of the slow part, the thing that you want to optimize for, and make sure you don't have to do that very often. And then on the sender side, so the inputs, you now have to collaborate with all the people who added an input to the transaction in order to sort of generate this shared secret, because now it depends on all the inputs. So for better Coinjoin support, so the initial problem that I pointed out is recipients can detect the input of the sender. So by using all the inputs, we solve that, and it's a speed up as well. And then the final issue, that I haven't really discussed yet, so maybe just go back briefly here, is that in order to generate the shared secret, you have to collaborate with all the Coinjoin participants, and now you're actually leaking to them that you want to send a payment to this person who has the public key of X. And we can solve for that with blind diffie-hellman. So this is a scheme that's also, I wrote this up probably a year ago, and Cashew, one of the eCash implementations, utilized this to do blind eCash. And it happens to also apply here, where you can blind the address that you want to pay to, ask the other Coinjoin participants to generate a shared secret based on this blinded key, and then you unblind it in the last step. And this allows you to sort of collaborate with your Coinjoin participants, get them to give you the data that you need in order to generate the silent payment address and not reveal anything to them. So this is what I talk about when I say, like, well, there's a little bit of extra Coinjoin complexity, but it ends up working quite nicely. Yeah, so there is a discrete log equivalence proof required to make sure that you know that the shared secret that you're being given is actually correct. So a little technical detail, but you know, if you don't have a check that you actually know that here S prime is actually small I times X prime, you have to have a proof that actually it is the multiplication of the two. Because if you don't get that proof, then someone could send you garbage data and the resulting silent payment address would be incorrect. So this brings me to a light client support. And so this is one where ultimately I think people should be running full nodes, and that's sort of the ideal situation in Bitcoin. But there are reasons to want to run light clients as well, and it's nice to be able to support that. So the interesting thing here is that what we can do is if we reduce the amount of scanning to, let's say, once every couple of months or something like this, then you can use the same trick that I was talking about earlier with the checking only the UTXO sets. What you can do now is you can say, like, between now and 3 months ago, you take all the transactions that have outputs that haven't been spent yet, and you only check those transactions. So the longer you wait, the more transactions will have been created and spent again. So the list of transactions that you actually have to check will be smaller the longer you wait. So by scanning only once every couple of months, you basically reduce the amount of work that a light client would have to do. And then the actual data that you need, you could naively, you would send like an entire block or all the blocks. But what we can do instead is just very specifically send the data that they need, which is for every transaction that has as of yet unspent output, combine all the public keys on the input side and only send that one input, that one combined input key to the light client and have them utilize that to check. And so obviously, so what I've described thus far is actually very slow. So now you would only notice that you got paid once every 3 months. And if you got paid, you wouldn't know. But what we can do is, because we have this sort of good way of eventually noticing that you're getting paid, we can now rely on sort of a less ideal method of notifying someone that they are getting paid. So let's say if I want to pay someone through silent payment address, through some other protocol, could be email, could be Nostr, could be whatever, I sent them a notification and say, like, hey, look, I paid you. Just pay attention to this specific location on the Bitcoin blockchain, and you will notice that you got paid. And so by doing this, basically you have sort of the best of both worlds, where you have an off-chain way of notifying people. You don't really care whether or not you actually manage to notify them, because like without the fallback of actually someone being able to scan the blockchain and finding all their payments, you would have this risk of like, well, what if they didn't receive my notification? And then if you have to kind of go and check and ask them, hey, did you receive my notification? Well, now you're interacting. And if you're interacting, you might as well just get an address from them. So this is sort of this method where you have an optimal case where you just send a notification, you just assume it arrives, and they will notice the payment right away. And if they didn't, they will catch it 3 months later. So finally, so here with the input keys, this basically allows you to generate all the possible outputs that you might have received a payment on. And then you need something like compact block filters to actually check, like, hey, does this block contain an output that belongs to me, yes or no? And you can even optimize this and use specific block filters. And instead of receiving a full block when you get a match, maybe just receive a list of all the outputs. So this can be optimized even further. But there's a lot of room here to actually make light clients viable. And yeah, so like I mentioned before, it's already super cheap today because there's not that many taproot outputs. And so at least we have sort of headroom to, like, as computers get better and as this protocol sort of matures, for now, it's just going to be super cheap, actually, to do light clients. So this brings me to payment labels. Yeah, I still have enough time. So payment labels are a way to sort of mark the recipient key. So the key X is sort of the silent payment address, the key that you receive money to, but you can add just a very basic integer to it, like 1 or 2 or 3, and very slightly tweak the key. And in doing so, the recipient can sort of scan for more than one key without doing all that much extra work, and sort of basically you're tagging your payment with a little label, a label that has just a number, an integer between 0 and 100 or something. And this is basically a way for the recipient to learn where or why a sender paid them. And so examples here are, if you have, you put your donation address on two different places, you put it on Twitter, you put it on GitHub, and now you can see like, well, which of these places did I receive more donations from? Or you were working on 2 projects and you want to know why people are donating to you. Are they donating to me because I'm working on project A? Are they donating to me because I'm working on project B? And with these labels, you can basically figure that out and so get a little bit extra information. What's very important here is that this is, and this is sort of something that trips people up, it is not a different identity, right? So if you create 2 of these different labels, people still know it's going to the same person. And so the reason for this is that you could have 2 identities. It's possible too. You could just create a second silent payment address, but now you're doubling your scanning requirements. So if you have 10 different identities, you do 10 times the work of figuring out whether or not you got paid. And so this is sort of an in-between solution where you get some information. It's not a different identity, but at least you can sort of figure out like, why are people paying me? So then this brings me to sort of comparison with with notification schemes, as sort of like generally it's being called. So there are a couple of schemes out there, BIP47 being one of the famous ones. And I think one of the big wins that I already alluded to is that payments are not linkable by the receiver, right? If I send money to the same recipient multiple times, they will not know the money came from me every time. They can't see the link. And in fact, with BIP47, it's slightly worse, where not only do you see the link, you also know the identity of the person that sent you money. So that's not ideal. And so I would argue that the silent payment scheme is ultimately sort of the best level of privacy we can get for these types of schemes. There's no on-chain notification needed. So the notification schemes, they rely on this idea of like notifying the recipient that you're going to send money to them and then telling them your public key. And you do this by just basically using the Bitcoin blockchain as a messaging system to attach your public keys. So like, hey, this is the public key that I'm going to use to send you payments in the future, so please pay attention. So without the notification, it's going to be more efficient, especially for one-time payments, because if you have to notify someone once, if you're only going to send one payment and you have to send a notification first, you're basically creating 2 transactions for a single payment. And unfortunately, the way it has been implemented, the notification can leak information about the fact that you are trying to pay someone. There are ways around this, but it's all a little bit messy. And so this sort of solves that problem entirely. Obviously, downside, to be fair to the comparison, is the scanning requirements and the like-line complexity I talked about. So where are we on progress with silent payments? So currently, I've been working on a BIP draft with Josie Bake, who's right there in the audience. And there's been an implementation which initially started off as a proof of concept by W0XLT, a pseudonym that I don't know who this person is, but they've been very helpful. Josie's been working with them quite a bit to make this proof of concept implementation into something that's actually viable to hopefully become possibly merged into Bitcoin Core. We welcome more help, so if anyone's interested, either approach Josie or me. We could use some help in the BIP review. The draft is pretty close to receiving initial review, but not quite there yet. And obviously in the code. There is, on Libera, there's a channel, Silent Payments, so you can join that if you want to be kept up to date with what we're doing and what's going on. And tomorrow, Josie's giving a workshop. I'm going to be there too, and also answer further questions. If not sure how much time we'll have here for questions. That's going to be at 1:15, and it's going to be basically a prototype of a mobile client in Python for asylum payments. So I can now either briefly go into these or go into questions. I'll briefly go into this. Okay, yeah. So one of the things that in the naive scheme that I explained so far, if you have a sender that is reusing their address, so their inputs are always going to be the same key, then you actually can end up with the same output. So if we go, see if I can go back here without too much effort. So let's say the naive scheme here. If on the input side, someone wants to send multiple payments to you, and every time they pick an input, the input key is exactly the same key because they're reusing addresses. Well, then the resulting output key is also going to be the same. So the way we can fix that is by taking the out point. So the out point being basically the reference of the output that you're spending. So on the input side, there's going to be a TXID and an index, and that is a unique number. So we take that number and we add that to the hash. And in doing so, every input, no matter if it reuses an address, will result in a unique hash here. And so we no longer have this problem where even if the sender is reusing addresses, the recipient won't have this problem of now having reused addresses as well. So a little bit of clicking here. We'll get there. Oh, there we go. Yeah. And then so here's another kind of like so just generally speaking, like there's a lot of like, because things change, we really had to sort of like rethink, like, well, what are all the things you can do in a regular payment, and how do silent payments sort of interfere with this? And so another thing you can do, normally speaking, is you could send money to a recipient in multiple outputs, right? If I get two addresses from someone, just interactively, I can create two outputs for them and it can send them money. But with the asylum payment scheme, you only get a single output per recipient. And so basically, if we want to allow, and this could be for privacy reasons, to give you an example, maybe in a Coinjoin, you want to send multiple outputs to a person in order to change the amounts in such a way that they get more privacy. What if you want to send multiple outputs within the same transaction to the same recipient? And so this can be solved by basically adding an index and using the index to 0, 1, 2 to generate different addresses. And once you get a hit on the index 0, you check whether index 1 is in there. If index 1 is in there, you check for index 2. And that way you can add multiple outputs with the silent payment scheme. And then kind of a final thing that I think is sort of a weakness of this scheme, and one that I haven't found a fully satisfying solution to, is that in the case where you are asking a third party to send money on your behalf to a silent payment address, they will have to know who it is that you're trying to pay. And this would not be the case. So imagine you have money on an exchange and you want to send money to maybe WikiLeaks or something, and they have a silent payment address. If they didn't have a silent payment address, you'd interact with them and they would give you a fresh key. You could just send from your exchange to that fresh key and the exchange wouldn't know who you're paying. But with the silent payment address, because the exchange has to actually generate the payments, they will find out, they will know who it is that you're trying to pay. So in the case of a third party where none of the inputs belong to you, you sort of have a bit of a privacy leak there. There is a half measure solution to this, which is that you can actually use the blind diffie-hellman scheme that I explained earlier. What happens then is that the senders, in this case the exchange, they wouldn't know who they are paying, but they could actually take every known silent payment address that's out there, check all of them, and then figure out who it is that you actually paid. So you're forcing them to do more work to figure out whether who you paid, but they can still figure it out. So this is sort of, I'd say, a half measure where if they're lazy, you maintain your privacy. If they really want to, they will figure it out. Yeah, so that concludes the presentation. If you want to know more, you can check out tiny.cc/Somsen. I gave a presentation a couple of months ago at TabConf where I actually sort of went in depth about alternatives to silent payments. So if you're interested in that, if you're more interested in like, well, what about BIP47? What about other alternatives out there? Private payments is another one. That is in that talk. So I have a link. Yeah, I put a link in here, so you can check out that talk if you're interested in sort of the alternatives and why I think ultimately silent payments are sort of the better solution of everything that's out there. So yeah, that concludes my talk. Thank you.